In this video, I'm going to be finishing off BC Homework 3.1. So we're going to start off with number 5. All right, the first one's asking us, we've got an object moving on the x-axis, and we've got its position. We've got a formula for position. We're going to write an equation for the velocity of the object at time t greater than or equal to 0. Okay, velocity is the derivative of position. That's going to be, I'm going to use power rule 15 plus 12t to the first minus 3t to the second. And then, okay, 5b asks us to find the times when the object is at rest, okay, and that's going to be when the velocity of the object is 0. Okay, so I'd say velocity is equal to 0 when negative 3t squared plus 12t plus 15 equals 0. Now we could factor out the 3 or the negative, or we could just divide both sides of this equation by negative 3. It's really the same thing. And divide everything by negative 3's. Minus 4t minus 5, that's going to equal 0. I can factor this. I can find two numbers that multiply to negative 5 and add to negative 4, t plus 1. Yeah. And that would be when t is equal to 5, only because we had said that, t was greater than or equal to 0. And then find the times when the object is moving to the left to give a reason for my answer. Well, for this one, if I've already found the zeros of velocity of the times when the object's at rest, okay, those would be the splitting times for when it's moving left and right. What we could do, we could actually make a graph of velocity. It's a downward-facing parabola. Now, this is tempting. Just be like, oh, 5 or negative 1 and 5, it's going to be like that. But remember, velocity was the downward-facing parabola. So it's going to look like that. Okay, the zeros are going to be at t equals negative 1 and t equals 5. But in reality, we know that t is really only greater than or equal to 0. So that's all we can see. Okay, so maybe put in a y-axis or something. That's going to be t equals 0. And, all right, so I'm going to say before t equals 5, I've got a positive velocity. Object's moving on the x-axis, so a positive velocity means it's moving to the right. Okay, moving to the left would be when t is greater than 5, and the reason for my answer would be v of t is less than 0. All right. Okay, that was number 5. Number 6 is another, object moving along an axis problem, but this time the object's moving along the y-axis. And so I'm seeing, okay, its velocity is negative 1 plus sine of 2t. We've got 2 different times and some positions at those times, because we don't really have the tools we need yet to recover that information from just velocity. All right, equation for the acceleration of the object at time t greater than or equal to 0. Well, acceleration is the derivative of velocity. So I'm going to take the derivative of negative 1 plus sine of 2t. So that'd be 0 plus 2 cosine of 2t. Right, and that's the acceleration at time t equals pi is the velocity of the object increasing or decreasing. Well, remember, we determine if something's increasing or decreasing by taking its derivative and checking the sign. So v prime of pi is going to equal 2 times the cosine of 2 pi. Now, 2 pi is a lot like 0, and cosine of 0 is 1, so we have 2 times 1. Okay, and I would say that velocity increasing is not the same as speed increasing, right? We'll have more to say about that in the next lesson. Velocity is going to be increasing because v prime is greater than 0. And then 6c, at t equals 2 pi, is the object moving toward or away from the origin. Okay, That's what we're going to need to consider the position and the velocity. And maybe we just draw ourselves a little diagram of that. Okay, at time t equals 2 pi, the object is moving along the y-axis. Draw this little y-axis here. Okay, at t equals 2 pi, the object is at the point 0, negative 1.283. So I'm just going to mark that right here, negative 1.283. That's obviously not an exact value. It keeps going. And what was I thinking here? Oh, we need the velocity at time t equals 2 pi. Okay, velocity is negative 1 plus the sine of 2 times t. So 2 times 2 pi would be 4 pi. Okay, 4 pi is again like 2 pi and 0, so sine of 0 is 0. Okay, negative 1 there. So the velocity is negative while the position is negative. That means I'm, down there and moving down, going away from the origin. Because the position and the velocity are both negative. All right, now number 7, showing us here's the graph of the derivative of f, not the original graph. Okay, so if we're asked about the critical points, critical point is when f prime equals 0 or when f prime fails to exist. Okay, so f prime is going to equal 0 at x equals negative 7, x equals negative 1, x equals 4, and x equals 8. And f prime is going to not exist never, right? F prime is a smooth curve. It's existing everywhere. There's no discontinuities or holes or anything, so then f doesn't have any places where it's not differentiable. Okay, for 8, where is f increasing? Well, that's when f prime of x is greater than, or you could do greater than or equal to 0, and that would be from negative 7 to negative 1. And also from 4 to 8. Okay. Then, number 9 said, for what values of x is f at a local minimum? Now, it doesn't say justify your answer, but we should always be in the practice of doing that. So I'm going to say minimum is going to be where f prime goes from negative to positive, because that causes the function f to go from decreasing to increasing. That would be right here at x equals negative 7, and then here at x equals 4. So x equals negative 7, x equals 4, and the reason is f prime changed signs from negative to positive. All right. And then my favorite question out of these is number 10, which is greater, f of 4 or f of negative 1? Okay, well, what you got to do is just be thinking about right here, okay, f prime of 4 equals 0, f prime of negative 1 is also 0, but that doesn't mean that the values of f at those x places will be equal. Okay, because you got to think about what's f been doing between x equals negative 1 and x equals 4. Okay, if f prime is negative this whole time, that means that f has been decreasing the whole time. So it decreased as x ran from negative 1 to 4. So that means that f has to be less at 4 than it was at negative 1. So I'm going to say f of negative 1 is greater because f prime is less than 0 on the interval negative 1 to 4. I think that's a pretty solid answer there. Okay. There's one page knocked out. Back here, right? An equation for the line. Okay, I think it's going to speed up. This is not going to be like that. The first 4 problems where there was a lot of parts and a lot of drill and algebra. Okay, so 11. We're going to need a point. Be x equals -1. G of -1 equals 0. Okay. Slope is going to be g prime of -1 is 3/2. So my equation would be y minus 0 equals 3/2 of x minus -1. Now find the values of x at which the graphs of f and g have horizontal tangent lines. Okay. It's going to have a horizontal tangent line when f prime equals 0. So that's going to be -1 and 0. D and E, there's no tangent line to put there, so it's probably going to be a sharp corner. 0, so that's negative x equals -1, x equals 0. Okay, and then I'll say G has a horizontal tangent line. Right there. So that would be at x equals 0. All right. If h of x equals f of x plus g of x, oh yeah, here's another good one, is h increasing or decreasing on the interval 1 to 3? Well, in order to determine that, we're going to need to take the first derivative of h, and that's going to be f prime of x plus g prime of x. And if we look on the interval 1 to 3, which is back up here, and we look at f prime and g prime, and we add them together, we're going to have a negative plus a negative. When you add two negative numbers together, you're going to get something even more negative. That's going to be decreasing. Okay. Then find the xy coordinates. I feel like there was definitely a missed opportunity there with where someplace where they had, yeah, I should have done like g minus f, and had it been negative or positive minus a negative is even more positive. There's definitely more potential with that question than I use. All right, so find the xy coordinates of the relative extrema of f. All right, so we need to be, using the first derivative test, seeing where the derivative changed signs. Here I'm going from negative to 0 to negative. That's not a sign change. Then negative to 0 to positive, that's an extremum. Okay, so, and it said f, right? Yeah, it just said extrema of f. All right, so I found one here where the derivative went from negative to positive, so that's going to be a local minimum at x equals 0. And the reason is f prime went from negative to positive. But then I've got here another sign change in f prime from positive to negative, and even though it's non-existing, okay, the function's existing there, so I know it's probably going to be like a sharp corner type thing, and so I'm going to say that's a local maximum. That was x equals 1 is a maximum. F prime changed signs from positive to negative. We don't really care that that the derivative itself didn't exist at that point, but it was still a sign change. All right. Now, number 15, the graph of g prime of x, the derivative of function g, is shown here in this figure. How many critical points does g have? How many extrema does g have? That's the question mark. That's too bad. Okay, critical points. Okay, critical points are places where the derivative either equals 0 or is undefined. I mean, I know it just says right here, this is the graph of g prime, but I just want to really re-emphasize, hey, we're not like counting the horizontal tangents, places where g prime is flat. Okay, not like that. The critical points are going to be 1, 2, 3, 4. This is the number of times g prime equals 0. But as far as extrema, which are local maxima or local minima, those are places where we have an actual sign change in g prime. So this one is not an extremum. Oops. Not an extremum. And so extrema would be only 3. Okay, because that one didn't count because I had no sign change in g prime. All right. Now, for number 16, f is this. The application of the mean value theorem to f guarantees a value where f prime equals some number. Okay, what's the value? Okay, what's the number that we're guaranteeing it equals? Well, remember the mean value theorem is if f is differentiable on the open interval 0 to 7 and continuous on the closed interval 0 to 7, that's really sloppy looking, then f prime of x equals, f of 7 minus average rate of change. Somewhere on the interval 0 to 7. Okay? So what we need to do is figure out this average rate of change right here. That's going to be the guaranteed value that f prime of x has to equal. So I'm just going to go ahead and do that off to the side. All right, so I need to figure out f of 7 minus f of 0 divided by 7 minus 0. All right, f of 7. 7 to the third minus 7 times 7 squared. Wait a second, that's another 7 to the third. That's going to zero out. Okay, plus 5 sevens is 35. Minus, when I plug in x equals 0, I'll have 0, 0, 0. Okay. It's like, okay, this is actually arithmetic I can do without a calculator. And so, okay, I get that. I get the average rate of change is 5, and it's like, oh yeah, well that's k equals 5. That's the value that we are guaranteed to have the derivative equaling somewhere. And that's probably a different problem for a different day, or maybe later on in this problem set. But we could actually go and have you find the derivative and set it equal to 5. And, if you were interested, that's how you would do it. X equals 0 is kind of on the boundary of our interval, so maybe 14 thirds is the place that we're looking for on the inside. But really, it says there's at least one place, so leave that there. Okay, now that's the end of that page. One more. Yeah, let me do this. So f is a function with f of 0 is this, f of 4 is the same number. How many values of x on the open interval 0 to 4 satisfy the conclusion of the mean value theorem applied to f on the interval 0 to 4? Well, I would say, actually, I'm just going to write on this one, last page. Well, first we should check the conditions to make sure we can apply the mean value theorem. And that's, okay, because f prime exists on 0 to 4, that means it's differentiable. So we can apply the mean value theorem. Okay, how many values satisfy the conclusion? Well, the conclusion is instantaneous rate of change. The derivative equals average rate of change. I might write off to the side, average rate of change is f of 4 minus f of 0 divided by 4 minus 0. And that's going to equal 0 because f did not change, right, as I went from 0 to 4. Now we know that obviously there was some weird stuff happening in the middle, but there was no net change. Okay, so how many values satisfy the conclusion? Okay, so I'm just trying to figure out how many times is f prime of x equals 0. And that's where x plus 2 multiplied by cosine of pi over 2x is equal to 0. Okay, that equals 0 only at x equals negative 2. That's not on the interval 0 to 4, so that's not going to really count for us. 0 to 4 would be like taking cosine from cosine of 0 to cosine of 2 pi. So I'm kind of thinking about the unit circle, whereas cosine equal to 0 up here and there. So that's cosine of pi over 2, that's x equals 1. And cosine of 3 pi over 2 also equals 0, that's x equals 3. Okay, those are both in the interval 0 to 4. So how many values? 2 values. Now, g of x, what value satisfies the conclusion of the mean value theorem applied to g? Okay, yeah. G is a polynomial, which means that it's continuous and differentiable for all x. So I can apply the mean value theorem. Okay, I'm going to first compute the average rate of change. G of 6 minus G of 0 divided by 6 minus 0. Well, G of 6 is going to equal 1/3 of 6 to the third. And we are going to be able to figure that out with our calculator, even if you don't know what 6 to the third is. And I'm realizing I do actually know what that is, but I'm not going to need it. Okay, so what we're going to do is we're going to say 6 times 6 divided by 3. And subtract 0, that's not really doing anything. And then divide by 6. Oh, wait a second, we can cancel that off. This is going to equal 2. And so rather than trying to do 216 divided by 3 and then divide by 6, again, 216 over 18. Wait, that doesn't seem right. Oh, well, yeah, that's because I needed an extra power of 6. It was 6 to the third. 1/3 of 6 to the third. Yeah, that would be 2 times 6, which is 12. Yeah, evidently 12 times 18 is 216. I didn't know that. And so what value of x satisfies the conclusion? Well, now I just need f or g prime of x equals 12. So that's going to equal x squared, and that's going to equal 12. That means x equals plus or minus the square root of 12, but in this interval, that's x equals positive square root of 12. All right, and this last problem here is just like determine whether we can use the mean value theorem. Okay, and remember, we can use the mean value theorem if the function is continuous on the closed interval and differentiable on the open interval. Okay, so that would be, we need, I'm going to just write it out once. All right, so we're just going to do some investigation on are these things continuous and or differentiable. Okay, x minus 1 to the 2/3. Okay, if you know what y equals x to the 2/3 graph looks like, it looks kind of like a bird. You know there's a sharp corner there. If you weren't certain, what you would do is say, take the derivative. F prime equals 2/3 of x minus 1 to the negative 2/3, which is like 2 over 3 times x minus 1 to the 2/3. If x equals 1, it's going to cause me to divide by 0. F prime won't exist. So no, not differentiable on the open interval. I found a place not differentiable at x equals 1. So for B, I've got f of x equals x plus 1. No, sharp corner at x equals negative 1. Okay, C, x minus 2's absolute value divided by x minus 2. Again, f's got a jump discontinuity. That's not continuous. So no. Discontinuous at x equals 2. You could also say it's not differentiable at x equals 2, and that would be because it's discontinuous. All right, D. I do actually think that this one we will be able to take mean value theorem on. Because it's continuous on -4 to 4 and differentiable on the open interval -4 to 4. The only bad thing that's going on with this function is here at x equals -5. Okay, it's going to cause me to divide by 0. So I'm just going to say yes for E. That'll be a no because we have a vertical asymptote at x equals -1. Okay. We got 3 more, but okay. So for F, x cubed over x squared minus 25. The only thing I could see going wrong here would be if x was either 5 or -5. That would cause me to divide by 0, but that's outside the interval I'm interested in. So I'm just going to say yes, I can apply the mean value theorem on the interval -4 to 4. But on the interval -6 to 6, absolutely not. No, they've got these vertical asymptotes here. That's going to cause a problem. And then H. This is one. Wait, I've done something wrong. Oh, I just totally skipped over this one. X squared minus 9. That one's a no because of the vertical asymptotes at 3 and -3. Okay, G was the one that was yes. Ahead of myself. And then H, we're going to need to draw a picture of H because this is exactly, I don't think I got to this situation in any of my classes, but this is like a very, very edge case of mean value theorem. So from -4 to 4, really what it looks like is, okay, we're x equals -4, we're at y equals 2. And at x equals +4, we're at y equals 2. But between -4 and 4, it's y equals x plus 1. So we expect to start off at -3 and go up to 5. I think it would look about like that. Okay. And if I was to just go in and, draw the graph of that function, this is the graph of f of x on the interval -4 to 4, I could draw, I don't know, it's not quite drawn scale, but it's x plus 1, so that's 1, that's going to be 2, see what I'm saying. And if we did the average rate of change of this function, f of b minus f of a divided by b minus a, then we would be seeing an average rate of change of 0. But the instantaneous rate of change of this function on the open interval is always +1. So mean value theorem wouldn't work here, right? Because there's no place where the slope is flat. But that's because we can't apply the mean value theorem because this is, although it is differentiable on the open interval -4 to 4, right? Ignoring those points, this thing is definitely differentiable at all points between -4 and 4. If we look over here, it's not continuous on the closed interval, and therefore we can't apply the mean value theorem. So that one, I'm going to say no because of the discontinuities at endpoints. Okay, but I got to say that this case right here, this like really, really edge case of mean value theorem, I do think this is a little beyond the scope of AP calculus. I just want to show you the limitations of the mean value theorem. Okay, so that's going to be all for this video. This was a very robust homework set. If you've watched both of the videos, you've done plenty of practice. That's all for this video. Thanks for watching.